G'day chemistry students, welcome to today's video. Today we are looking at dot point 2.2.3. We're looking at some simple mole calculations, which is the first time that we get to work with the mole and see how we can use it quantitatively. This is going to form the basis of a lot of the problem solving and calculations that we'll be completing throughout this entire course, not just for Module 2. Let's get stuck into it. Now, first off, you'll find that these activities that I'm going to be showing you are best completed if you have a periodic table and a data sheet with you. If you don't, it's not the worst thing in the world. I will talk about everything that I'm looking at, but certainly will assist if you can see what I'm referring to on the table and the data sheet as I go. Now, first off, we looked at this guy in the last video, the Avogadro constant. It is the number of particles or the number of atoms or whatever we're looking at in particular that represents the mole itself. So in the same way that a dozen, the word represents the number 12 and a decade represents the number 10, a mole represents 6.022 times 10 to the 23 particles. And there's actually a formula which exists that relates the Avogadro constant Na to the number of moles of whatever you're counting or whatever you have. It's not in your data sheet. It's something that you need to sort of know yourselves. It doesn't come up all that often, but it certainly can come up from time to time. And that formula is this, that the number of moles is equal to the number of particles that you have, or the number of whatever you're counting that you have, divided by the Avogadro number. And so if we were to write that using our pronumerals and appropriate notation, that would be N for the number of moles is equal to the number of particles, capital N, divided by Na, the Avogadro number. Now, to keep this in mind as well, that N has the units MOL for number of moles. The other two are unitless. They are just counts of particles, essentially. The other formula that we're going to be using today is the first one in your formula sheet, which is this guy here, N equals M over MM. This is that the number of moles, again, little n, is equal to the mass of the substance that you're looking at divided by its molar mass. Now, this will make a little bit more sense when I do a couple of practice problems with this guy. The one thing that's really important to keep in mind is that, first off, the molar mass is this here, mm, and the mass of the substance is m. And the molar mass is actually the same number as our atomic weight as we've looked at before. So we've measured atomic weight for the mass of a single atom, but it also converts to the mass of a mole of a particular substance. So for example, if I had a mole of hydrogen atoms, it would weigh exactly 1.008 grams. Just to keep in mind as well, some key units. Again, N is written in MOL. Mass of the substance is always in grams, and that is because our molar mass is written as grams per mole. And it looks like that. So it's grams times moles to the -1, or grams per mole. Let's get stuck into some calculations. So in these first two calculations, what we're going to be aiming to do is do some conversions between number of moles and number of particles, whether we're looking at single atoms or molecules. So in the first question, what we have written here is that if there are 3.11 times 10 to the 14 atoms of zinc, how many moles of zinc are there? And to make this conversion, we need to be using our N equals big N on Na equation. So again, N is the number of moles, big N is the number of particles, and Na is the Avogadro constant. So currently, we've been given in the question big N, that we have 3.11 times 10 to the 14 atoms. We also know always the Avogadro constant, Na is 6.022 times 10 to the 23. And what we're trying to find is the number of moles, and that's missing. Now, our equation is already set up in a way in which the number of moles is the subject. So if that's the case, then all we have to do is substitute and go from there. So we know that the number of moles is equal to 3.11 times 10 to the 14, all over 6.022 times 10 to the 23. And all we have to do is put that into our calculator and get our number. So I can write in 3.11, and then I'm going to multiply, and I've got this 10 to the power of here on my calculator. It might be a little bit difficult to see in this light. That might be a bit better. This guy here, 10 to the power of, give that a sec. So this guy here in that gold color can be selected if I hit shift and then that button, and then that gives me a 10 to the power of, and I'm going to put 14. And I've forgotten to put all of this as a fraction actually, so I'll see if I can do it. It's not working, so let me redo that from the beginning. 3.11 times 10 to the 14, and I'm going to drop down and write my other number down the bottom, 6.022 times 10 to the 23. When I hit equals, I can see that my number is 5.16 times 10 to the negative 10 moles. So significantly smaller than a single mole, and that's to be expected. The number of particles that we had was significantly lower than the Avogadro constant anyway. Now looking at the second question, we're sort of going to be going in the reverse order. Here the question says 6.2 moles of water was poured into a beaker. How many, and that probably should say, anyway, ignore that, that's fine. 6.2 moles of water was poured into a beaker. How many water molecules are there? So again, we're going to be using our N equals N over NA equation. What we've been given this time, though, is the number of moles rather than the number of particles, and that's equal to 6.2. We also know the Avogadro constant, Na, is 6.022 times 10 to the 23. And what's missing is N. So what we need to do first before we do any kind of substitution or calculation is to rearrange the equation so that big N is the subject alone and by itself on one side. Now if I multiply by the Avogadro constant on both sides, what I'll end up with is big N alone and by itself on one side, and then N times the Avogadro constant on the other. And so what we can do is substitute our two values that we know into the right hand side of our equation and calculate for big N, which is the number of particles, in this case the number of water molecules. So 6.2 times 6.022 times 10 to the 23. Again, I can put that in my calculator. So here I'll put in 6.2 times 6.022 times 10 to the 23. And the number of particles that I have is 3.73 times 10 to the 24. And that would be water molecules. Now, in a moment, I'm going to flip the page. I have a few more questions, and these should show us how we can go about converting from number of moles to mass and vice versa. Just give me a sec, and I'll flip the page over.